Okay, so last time we talked about certain kinds of maps from R2 to R2 and we called these the rigid motions of the plane. And we studied a few examples. So, the kinds we looked at were maps which we called translations, then there were reflections, we looked at rotations. So, these were all examples of maps which had the following property, that they did not change either lengths or angles. So, they sort of just moved the plane in some rigid fashion, and we also studied things like invariant figures under these types of maps and so on. So, now what we want to do next is to talk about non-rigid motions. So, let us again start doing these by examples. So, now we look at things which do not preserve lengths or angles or things like that in general. So, the first example will be the following map. So, remember we are looking at maps from the plane to the plane. So, let us define f to be the function which takes the point x comma y on the plane to the point let us say 3x comma 2y. So, for a start let us say 2x comma 2y, which is again a point on the plane, and let us try and study what this function does. Okay. So, at the outset all it does is multiply the x coordinate by 2 and multiply the y coordinate by 2. Now, what this does geometrically speaking is the following: it takes this point x comma y, so I have just joined it by a line segment to the origin, and it maps this point to the point along the same line but twice as far. So, it maps it to the point 2x comma 2y. So, this is how we should think of the function. It takes this point xy and sort of blows it up by a factor of 2 or stretches that line segment by a factor of 2 and maps it to the endpoint of the resulting line segment. So, this is sometimes called a dilation or a stretch by a factor of 2, okay, dilation by a factor of 2. So, dilation here is a word which is used to mean either sort of a stretch or a shrink by some factor. Okay, so, let us do the same sort of analysis that we did for the rigid motions, which is to try and understand what this map does to other kinds of figures on the plane. So, for instance, let us study the effect of this map on lines. Okay, so, I will take a typical line on the plane. So, let us say here is a line on the plane, and what we want to do is to apply this function f to each point of this line. Okay, so, you take each point of this line, apply the function f, you get a new point, and you join all the resulting new points and see what sort of figure it becomes. Okay, so, for instance, from here it appears if you take this point here on the y axis, the function doubles this distance, it maps it to something again on the y axis, but twice as far. Similarly, this point on the x axis will map to something along the x axis, but which is twice the distance from here, and the same sort of holds for every point in the middle. You just join it to the origin and sort of blow it up by a factor of 2. Okay, so, this point maps to this point, so on. So, if you sort of try and join these, what you will find is that it is again a line. Okay, it is a line, but sort of twice as far from the origin as the original line. Of course, this is just a pictorial thing, you know, I have not really justified this. You could try and convince yourself of this by plotting a few points and so on, but of course, the most conclusive proof is really by writing down actual equations and checking that this function does indeed map a line to a line. Okay, so, how does one go about checking things like this? So, here is the well, let us do the following. Let us call this function xy, what it maps to, the point xy, the image of the point xy under this map, let us call it x prime comma y prime. So, you want to think of this function as sort of sending points here to points So, it maps it to a point whose coordinates are now x dash y dash. So, this point here is x y. Okay. So just remove the x y from here to avoid confusion. That is what the function does. So, now let us do the following, let us figure out what this becomes on the new axis. So, first let me take a line here. So, I will take a line L. So, what is the equation, typical equation of a line? Well, there are many different ways of writing it, but say here is one familiar form of the equation of a line. Let us call it y equals mx plus c. Right. So, this is the equation of the line. So, the line L satisfies this equation, has equation y equals mx plus c. In other words, a typical point x comma y which lies on this line will satisfy this equation. Okay. So, that is what it means to say that the line has this equation. So, let us take a point x comma y on this line L. So, in other words, x y satisfy this equation and apply the function f to it. Okay. So, I will apply f to this point x y, thereby obtaining another point x prime y prime on the plane. And the question now really is the following: as you let x comma y vary along this line, as you move them, as you move this point along the line, you want to know how x prime y prime changes, right? How does that move? In other words, if you know the equation that x comma y satisfies, can you somehow deduce an equation that x prime y prime satisfies? That is really the question here. So, let us try and deduce this. So, what is x prime? By definition it is 2x, y prime by definition is 2y. Okay. Now, we know x and y satisfy this relation. So, that automatically gives you a relation for x prime y prime, because x is nothing but x prime divided by 2 and y is nothing but y prime divided by 2. Okay. So, from this you conclude the following: y prime divided by 2, which is basically y, must be the same as m times x, which is x prime divided by 2 plus c. Okay. So, observe that the point x prime comma y prime satisfies that new equation here, which of course you can simplify to y prime equals m times x prime plus 2c. Okay. So, this new equation is again the equation of a line, which we will now call L dash, the line L dash, and this new line, observe, is, well, it's the equation looks more or less like the old line L, except that c is replaced by 2c. Okay. So, remembering that c is sort of like the y intercept, it is a line whose y intercept is twice the y intercept of the original line, if you wish. Okay. So, lines map to lines, that is sort of the moral of this analysis. Lines map under this function f back to lines. Okay. So, that is one aspect of what this map does, the dilation map. And of course, so it is sort of also easy to see what other sorts of figures would transform to under this map. For instance, if you take a circle, say of radius 1 or say any arbitrary radius r, and apply this function f to it. So, if this circle has radius r, then what the function is going to do to each point of the circle is it is going to map it to a point which is at a distance 2r from the origin. So, all you are going to get is a circle whose radius is twice the original radius. Okay, so this is now a circle whose radius is 2r. So, that is going to be the image of this circle under this map f. Okay, so somewhat better circle. So, let us call it circle of radius 2r. And of course, well, other kinds of figures, sort of triangles and so on. So, if say this were a triangle on the plane, then let us do the following. Let us think of what this function does. So, imagine joining the 3 vertices to the origin in this way, and what this function does, of course, is to dilate it by a factor of 2. It sort of pushes everything out by a factor of 2. So, imagine now extending these lines, all of them to double the length, and the resulting 3 points are the images of the vertices of the original triangle. Now observe, whenever you want to figure out the image of some sort of polygonal region, say a region which is bounded by lines. So for instance here it is a triangle. If I want to know what happens to this triangle under this map F, it is actually enough to just figure out what happens to the 3 vertices. Okay. So if I have the 3 vertices A, B and C, they map to, let us call them A prime, B prime and C prime. Now A maps to A prime, B maps to B prime, and we now know the one sort of important fact that this map sends lines to lines. So the line joining AB must therefore go again to some line, and it must therefore be the line joining A prime and B prime, because a line is uniquely determined as soon as you know 2 points on the line. Okay. So this line had better map to this line, there are no choices. Similarly B maps to B prime, C maps to C prime, the line BC must map to some line, that is the other fact we know, therefore it must map to the line joining B prime and C prime. Similarly, okay. So at least somewhat convincing argument I hope, which tells you that this triangle here will just map to this somewhat bigger triangle. And notice that this bigger triangle here has all side lengths being twice the original side lengths. Okay. So you can see this by using similar triangles, for instance, if that is familiar. The angles remain the same. So these angles are all preserved, the same angles as in the original triangle, but all side lengths are now twice the original side lengths. Okay. And to prove this, for instance, you need to use some elementary similar triangles, because the side OA is half the length of the side OA dash. Okay. So you will sort of have to play with some similar triangles here. So I will leave that as an exercise for you, but observe that this triangle A dash, B dash, C dash has, well, let us just write it like this, is similar to the original triangle ABC, and all side lengths are double. Okay. Angles of course remain the same, because that is sort of one of the important properties of similar triangles. Okay. So lengths double, angles remain the same, and notice that what happens to the areas. So what does this transformation do to areas? So that is the sort of the final point to note, what happens to area. So observe that if I have a circle of radius r, its area is pi r squared, and the circle of radius 2r has area which is 4 times pi r squared, because I need to do pi times 2r whole squared. So this resulting bigger circle here has 4 times the area. Similarly, in the case of the triangle, all side lengths are double. So if you wish, the altitude of the triangle will also be double the original altitude, and so the area, which is sort of half base times altitude, is also multiplied by a factor of 4. Okay. So areas get multiplied by a factor of 4. Okay. So lengths get multiplied by a factor of 2, area gets multiplied by a factor of 4, angles remain unchanged. So those are the various features of this particular map, which sends everything to twice itself. So it is a dilation, sometimes called a uniform dilation by a factor of 2. Now let us take another example. So this is sometimes called an inhomogeneous dilation. So just tweak this slightly. Here is example 2, we can call an inhomogeneous dilation. So what does this do? Well, f of x comma y is, for instance, 3x comma 2y. So here is an example of a map which sends xy to 3x comma 2y. So to really understand why I called it an inhomogeneous dilation or a non-uniform dilation, so imagine what this map does to, say, a square of side length 1. So imagine I have a square here, 1 0 0 1 1 1, that is the origin. So the first fact here is again that lines map to lines. Okay, so this dilation, this inhomogeneous dilation has the same property that it maps lines to lines. So lines map to lines. Okay, so that I will leave as an exercise for you to check pretty much by using the same calculation, which is you write down an equation of a line. So you take a point x y on that line and then you figure out what equation x prime and y prime satisfy. X prime is 3x and y prime is 2y. So maybe we'll in fact do this in a minute, because we also want to see what happens to angles. So the key thing here is if you take a square of side length 1 and you map, you figure out what happens to it under this map. So here's what you will notice, that the point 1 comma 0 maps to the point 3 comma 0 and the point 0 0 1 maps to 0 2. So what you are going to get now is no longer a square but rather a rectangle. Okay, so and the point 1 comma 1, if you sort of figure out what it does, it goes to 3 comma 2. Right. So the square of side 1 has now become a rectangle of sides 3 and 2. This was originally 1 and 1. So this is the reason why I am calling it an inhomogeneous dilation, meaning it is sort of like a dilation, but it is a dilation by different amounts along different directions. So the x axis suffers a dilation by a factor of 3, whereas the y axis is only stretched by a factor of 2. Okay, so the stretching factors are different along different directions, and of course, so the shapes of the original figures are very much going to be distorted. So a square here, for instance, becomes a rectangle. Similarly, if you try to figure out what happens to a circle of say radius 1, like we did in the earlier example. So again, along the x axis it gets stretched by a factor of 3, along the y axis by a factor of 2, and what you therefore get is in fact an ellipse with major axis 3 and minor axis 2. Okay, so this map actually sends a circle to an ellipse. Okay, so again a result of the fact that it is stretching differently along different directions. And the other important thing is that angles, so what can we say about lengths in this case? As we said, lengths do get stretched, but by different amounts along different directions, so we can't say much more than that. So the various facts, lengths get dilated by different amounts along different directions. So dilated differently along different directions. Angles, so let us consider angles. So here is an important feature of this, angles are not preserved anymore. Okay. So we looked at the earlier case of a dilation, uniform dilation by a factor of 2, that mapped any figure to a similar figure, okay, where all the angles ended up being preserved. If you try doing this to the inhomogeneous dilation, you will find that angles are not preserved. So here is an example. Let us take the line, just the x axis, that is one of the lines, and let us take the line y equals x as the line L2. So that makes a 45-degree angle. So here is a 45-degree angle between the lines L1 and L2. And now if you figure out what happens to these two lines under this inhomogeneous dilation, so L1 just maps back to L1. So I am just going to tell you the answer, check that this is in fact correct. L1, the x axis maps back to the x axis, whereas the line L2 whose slope is 1, okay, y equals x, now maps to something of slope 2 by 3. Okay, so it will sort of move a little closer to the x axis. So this is what happens to the line L2. So check that L2 becomes a line whose slope is 2 by 3. The original slope here is y equals x, so that has slope 1. So, this angle here theta is strictly smaller than 45 degrees. So, what it is done is because of this sort of stretching differently along the two different directions, it has ended up making the angle different. Okay. So, here is an example where angles are not preserved. It is pretty much our first example, because of course, the rigid motions that we talked about last time preserve everything. They preserve lengths, angles, areas, pretty much everything you can think of, they end up preserving. Dilations, they do not preserve lengths, of course, they do not preserve areas, but they do preserve angles. Okay. Now, inhomogeneous dilations are the first examples of things which also do not preserve angles. Okay. They distort things sufficiently that even angles change. And of course, we talked about lengths, angles, and so what about areas? Okay, so let us just look at the two examples of figures which get transformed under this map. So, one we said we take a square of side 1, it becomes a rectangle of sides 3 and 2. So, the area here is a 1, whereas there it is a 6. Similarly, a circle here of radius 1 has area pi r squared, so it is pi, whereas the ellipse has area, well, it may not have a formula which is very well known, but the area of an ellipse, if you know the minor and major axes, so the area of an ellipse turns out to be pi times, instead of r squared, it is a into b, where a and b are the minor and major axes. Okay, so, in this case, the area of this ellipse is pi times 3 times 2, okay, so that is 6 pi. So, observe again that the ellipse has area which is 6 times the area of the original circle. Okay. So, both this the square becomes a rectangle of area which is 6 times, the circle becomes an ellipse again whose area is 6 times. So, the areas in fact get multiplied by a factor of 6. So, areas, at least looking at our two examples. So, I am not really proving anything here, it seems at least from these examples that the area is multiplied by a factor of 6. So, those are the features again of the inhomogeneous dilation. Now, let us do one more example. Example 3, the function f of x y just defined to be x minus y comma x plus y. So, here is a formula for what the function does. Again, let us study this pretty much using the same sets of points. So, for a start, what does this function do to lines on the plane? And again, I claim that lines map to lines. Okay, so again, exercise, check that this is in fact correct. So, it is very similar to everything we have seen until now, in the sense that lines certainly map to lines. Okay. So, that of course makes it easier to figure out what it does to polygonal regions, regions which are bounded by lines. So, let us do that next. So, again I will take a square of side 1, let's take so, here are the 4 vertices of a square of side 1, and let us figure out what happens to each of these 4 points under this transformation f. So, let us apply the transformation f to this. So, for a start, let us apply, so observe that the origin 0 comma 0, if I apply f to it, I will just get 0 minus 0, 0 plus 0. So, the origin goes to the origin. So, the origin just remains where it is. The point 1 comma 0 maps to 1 minus 0 and 1 plus 0. So, that is just 1 comma 1. So, the point 1 1 is one of the vertices. Now, the point 1 comma 1 under this map maps to 0 comma 2. So, that is now a point on the y axis. So, so far here is what I have gotten, one of the sides is like this, the other side is like that, and if you look at what happens to the third point 0 comma 1, that maps to minus 1 comma 1. So, that is this guy. Okay. And again, as we said, if you figure out what happens to the 4 vertices, you are more or less done, because the line segment joining them has no choice but to map to the line segment joining the resulting points. Okay. So, what we have really is this maps to this square here, and observe that what is this? This is again a square, but the square has side which is, well, what is the length of this side? It is square root 2 times the length of this side. So, this is a square of side 1, whereas this is a square of side root 2. Okay. And well, what else is there? The area therefore is, so what happens to areas? The area of this square becomes twice, area equals twice the original area. Okay. And what else seems to be happening here? So, the length of this line segment, this was a line segment of length 1, it mapped to a line segment whose length is square root 2 times. So, length is dilated by a factor of square root 2. Okay. So, at least for this square, all of these sides are of length 1 and the resulting sides there have length square root 2. Okay. So, it seems at least that the length of line segments is multiplied by a factor of square root 2, therefore, the area is multiplied by a factor of 2, but one nice thing here seems to be the angles are unchanged. So, the angles, this was a square and well, that seems to remain a square in the other case as well, right. So, at least in this example the angles are unchanged, and but at the same time observe this has, this is sort of the kind of thing that happened when you had dilations. When you dilated something by a factor of square root 2, you would pretty much have all these things happening. Lengths go up by square root 2, angles do not change, area becomes twice and so on. But this map is clearly not just a dilation, right. A dilation would have multiplied this, would have mapped this square just to a square along the x and the y axis of side length root 2. Instead, this is mapping it to some sort of a rotated square. Okay. So, you still have a square, but it is rotated by an angle 45 degrees. So, observe this is a 45 degree angle. Okay. So, what it seems to be really is the following, and we will look at this next time. This map F really does two things at once. Okay. The first thing it does is it takes the original square here and rotates it by an angle of 45 degrees, and then it dilates lengths by a factor of square root 2. Okay. So, at least here is what it seems like F is doing. It is doing two things. First, it is a rotation. So, F seems to have the following description. It seems like a rotation by 45 degrees, at least for the unit square, followed by a dilation, followed by dilation by a factor of root 2. So, it is some sort of a composite map, it is something which achieves two things at once, and so we will see that the natural way to think about this is in terms of compositions. Okay. So, we will in fact revisit what compositions mean and rewrite F in terms of a composition of two maps. Okay. So, this is something we will do next time.